So today we're going to talk about a second method for finding absolute maxes and mins. Our critical point endpoint method, as you recall, amounts to, first of all, identifying the candidates, which are the critical points and endpoints. And then second of all, evaluating our function f at each candidate. The largest one is the max, the smallest one is the min, we're done. It turns out that the critical point endpoint method is not always applicable. In particular, I cannot use it if my domain is an open interval or if it is unbounded. We cannot use the critical point endpoint method if the domain is open or unbounded. And so in those circumstances, there's another tool that is available to us, and that is to consider the sign of f prime. So today's theorem is called the argument from the sign of f prime. And I want you to consider a function. I want you to consider a function that has a derivative whose number line looks like this. Now, if I asked you to draw the function based on this number line, I see you guys moving your hands, good, then you would say that that function is increasing for x is less than c, and it is decreasing for x is greater than c. And therefore, it is absolutely necessary that f of c is the absolute maximum value of the function. Why? Because f prime is positive for all x less than c. And it is negative for all x greater than c. And that is our argument from the sign of f prime. Now, every year, students get this confused with another test that we have. They get it confused with the first D test. But there are two crucial differences that are related to the first D test. First of all, what does the first D test find for us? It finds local extrema. That's right. It finds local maxes. So the argument from the sign of f prime is not finding a local max, it's finding an absolute or global max. And corresponding to that, what's the condition for the first D test? F prime of c has to change sign at x equals c. That's not what's going on here. I'm not looking just in a neighborhood around x equals c. I'm looking at the entire domain, and I'm saying that f prime is positive on the entire domain up to c, and negative on the entire domain at c. And because of that, my function is increasing on the entire domain up to c and decreasing thereafter. So f of c must be the biggest point. Yes?
What is the difference between absolute max and local?
An absolute max is the largest value on the domain. Whereas a local max is going to be the largest value on an open interval containing x equals c.
So for this one, C is the local max, but also absolute.
F of c is, yes. We always say that the f values are the maxes, right? Well, you can imagine that this argument can be turned around so that I can also argue that if f prime is negative for x is less than c, and positive for x is greater than c, then f of c is an absolute minimum. F of c is an absolute minimum. Now, I'd like to show you how this works out by considering problem number 16 in your book on page 227. And what I will do is actually type this problem in so that it's clear. What are the dimensions of the lightest open top, how do they describe this? Right circular cylindrical can that can hold 1,000 centimeters cubed of liquid. And that's the whole question. So we want to consider now how we would translate this question into math. And our basic plan is that we're going to create a function, identify the domain, and then based upon the function in the domain, choose either the critical point endpoint method or the argument from the sign of f prime in order to do our analysis. That's the plan. Let me write that down. Function, domain, choose critical point endpoint or argument with the sign of f. And this is the basic plan for all of the problems that we are doing all this week. Now, first of all, when we see the word dimensions here, dimensions are asking about the important measurements. So in this particular case, we're talking about a can, and they describe the can as right circular cylindrical. So let's see what that means here. Circular, pretty obvious. Cylindrical means that it is constant all the way down. And right means that it is straight up and down and not tilted. So that we have a can that looks like this. Just like that. But they also describe that can as being open top, which means that we're going to use metal for the bottom, but we're going to have it open on the top. It's really a cup, is what it really is. So when we talk about the dimensions of this can, we're talking about the things that we would measure about it, the height, and also the diameter or radius. It's a little bit easier to work with the radius than it is to work with the diameter. And these are the dimensions here that they're asking for. Does that make sense to everybody? The thing I want you to pick up on are the words that are being used here and their meanings. So if you have any questions about those words, now is the time. Yes? Ah, great question. The word lightest is really interesting because clearly they want us to find some kind of minimum, and the minimum is the minimum of the weight of the can. What is it that makes the can heavier or lighter? Good. The material, the surface area. That's exactly it. So what we're really trying to do is to minimize the total area, surface area of the can. That's the function we want to minimize. So let's construct that function. We want the minimum of the surface area. And we're going to walk through and do some simple geometry to make it happen. Where do I have material on my can? Well, first of all, I have it on the bottom. And that bottom is the shape of a circle, so its area is pi r squared. We call that the end cap, or the base. Then we're going to add onto it the area around, which we call the lateral area. To get the lateral area, we're going to employ a trick. Imagine for a minute I take a mathematical knife and I take this can and I slit it right down the side and I open it up and unroll it. And when I open it up and unroll it, what shape do I get? Rectangle, that's right. And the rectangle has a height of h. What is the length of that rectangle? It's the circumference of the circle, which is 2 pi r. That's right. That's my can when I unroll it. Does that make sense? And therefore, the area here is 2 pi times r times h. This is the function that I want to make a minimum. I have a function, 4. But I also have two variables in my function, h and r, so I need an additional condition in order to constrain the h and the r. What is that additional condition? Ah, that's right. It can hold 1,000 centimeters cubed of liquid, and either the units or just experience can tell you that we're talking about the volume. What is the volume of this right circular cylindrical container? That's right. Take that base and multiply it through h. So the volume, we take our diagram right here and move it to there. All of it. So the volume then is 1,000, and that is equal to the area of the base times the height. And we are going to use this equation to substitute out one of the variables in our function. And I like h because it's the easiest to solve. Now replace that in here, then what I get is that the surface area is equal to pi r squared plus 2 pi r times 1,000 over pi r squared. And I have the good fortune that the pi's cancel and one factor of r cancels, so that when the dust settles, I get pi r squared plus 2 times 1,000 over r. And that is my surface area function as a function of radius r. Question: what's the domain? What is the smallest value that I can have for the radius r?
0.
Close to 0, right? Any value up to but not including 0, right? So our domain is the open set starting at 0, not including 0. Notice, Mark, you almost said 1, but then you realize that there are a whole lot of numbers between 0 and 1. What is the largest theoretical possible radius? Close to 1,000? I can do bigger than that. I can make a radius 2,000. There is no largest possible radius in there. So the domain is actually all the way out to infinity. if I were to have a radius of 0, or if I were to take the limit as the radius goes to 0, my can would get infinitesimally skinny. Right? It would be really, really long because it's got to hold 1,000 centimeters cubed worth of liquid. So at some point it's like a pipette or something that stretches it way out. Okay? On the other hand, if I let r go to infinity, then my can is going to get really, really flat, like so, and wide. So that at some point it's more of like a holding tank than it is a can, and then as it gets even wider than that, it just becomes like a puddle. Okay? So somewhere in between here, we're going to have a minimum surface area. All right. And here's the observation that I want to make. Because the domain is open, and also because it is unbounded, especially because it is unbounded, therefore I cannot use the critical point endpoint method. I must use f prime, the argument from the sign of f prime. Because of the domain. So I'm going to do that by evaluating the critical points here, and I'm hoping that there's only one of them. So let's do that. Walk through. What is DSDR?
2 pi r minus 2,000 pi to the negative 3.
Very good. That's exactly right. He's thinking of 2,000 over r as 2,000 r to the minus 1 power. And now we're going to set that equal to 0. And we're going to clear the fractions by multiplying those sides by r squared. And when I multiply those sides by r squared, this side I get 2 pi r cubed minus 2,000. And on this side, 0 times r squared is still 0. So the r cubed is 2,000 over 2 pi, 4,000 over pi, and r is the cube root of 1,000 over pi. That's an interesting critical point right there. I could find a decimal approximation if I wanted to, but I'm not really interested in doing that. So now let me evaluate the sign of DSDR, or I could write it as S prime. And here is my critical point. And my domain stretches all the way from 0 out to infinity. So let me evaluate this by plugging in a value somewhere between 0 and the cube root of 1,000 over pi. Now I don't know what the cube root of 1,000 over pi is any more than you do, but I'm pretty sure it's bigger than 1. Because 1,000 over pi is bigger than 1 and cube root, right? So let me try r equals 1. And when I plug that in here, I get 2 pi minus 2,000, which is definitely right. And again, I don't know what the cube root of 1,000 over pi is, but I know it's less than 1,000,000. So in my mind, I imagine plugging in 1,000,000 into DSDR. And when I do, 2 pi times 1,000,000 minus 2,000 over 1,000,000 squared is going to be pretty positive. So I don't have to work too hard to evaluate here, even though I'm dealing with unfamiliar numbers. You see what I'm saying?
Was this always with different signs?
Not necessarily.
What do you have the same sign?
Then you don't have an absolute maximum. Yeah. So I would interpret this now as saying that because s prime is less than 0 for r less than whatever it is, and because s prime is greater than 0 for r greater than whatever it is, therefore I conclude s is a minimum. Let's just check that and make sure that it makes sense. Yes, we are decreasing, then increasing. So minimum is a minimum at r equals this guy right here. And we already have a relationship between h and r. H is 1,000 over pi r squared. So I'm going to represent that as 1,000 over pi times r squared. And I don't really need to simplify that, although I can. If I choose to simplify it, it would look like this. I would rewrite the division as multiplying by the reciprocal. And I would rewrite the exponents in terms of fractional exponents. Everybody see what I'm doing there? And then I would subtract the exponents so that I get the cube root of 1,000 over the cube root of pi. Which, interestingly, turns out to be exactly the same dimension as r. So this cylinder is kind of cubish, very squat. Which makes you wonder, how come it is that soft drink manufacturers don't make their cans shorter? Because they would use less material that way. Any ideas? There's a really simple reason. It would look a little weird, but you'd get used to it. What's the most important thing about a can that holds a beverage that somebody's going to drink? I don't know about the most important thing, but one important design requirement. It has to fit in your hand. And if we made the can any shorter, then it would have trouble fitting in your hand and being drinkable or not. Yeah. Yes.
Is there any case that you can't use argument?
That's a great question. He would love to have just one tool instead of two, right? So, yes, if I have two critical points, then it's entirely possible that my f prime would be on negative, positive, negative, and then I wouldn't necessarily know whether or not that minimum was a legitimate thing. So if you have more than one critical point, the argument from sine of f prime is problematic.
But what about you have two critical points, one without equal weight?
Then that would actually work. You really only have one critical point there. Yeah. Good. Let's take a look at a second problem.
But this one, why did the yesterday we had a rectangle and we can actually make it like
Well, if you take a look at s as a function of r, you can see that if I actually let r be 0, then I actually have to have an infinite length in order to make that happen, because I'm constrained by the need to hold 1,000 cubic centimeters. So here, as r goes to 0, s actually goes out to infinity. Okay, let's consider problem number 13 on that same page. You are designing a rectangular poster to contain 50 square inches of printing, with a 4-inch margin at the top and bottom, and a 2-inch margin on each side. What overall dimensions will minimize the amount of paper used? Okay. I want to consider what's happening here. First of all, we have a rectangular poster. Let's go ahead and draw that. Where's my rectangular poster? Well, the rounded edges. There's my rectangular poster. Now, I do not know the length and width of that poster, right? So I'm going to have to call the length and width something like X and Y, or L and W, I don't know. Then we are told that there is a 4-inch margin on each top and bottom, and a 2-inch margin on each side. What that means is that around the boundaries here, we have a certain amount of border that goes into the total amount of paper that is going to be used. This is where the text happens, and the margin is extra paper that's used. And what I also know is that the area on the inside is 50 square inches. And so what we want to do is to minimize the amount of paper used. In other words, we want a minimum of what function? Well, x times y does equal 50. That's a good point. But that's not the minimum that I'm trying to find. How do you...
Plus 4 times y plus 8.
Yes, in other words, area. I'm trying to minimize the total area of the whole thing. And the total area of the whole thing is this dimension, which is y plus 8, top and bottom, times this dimension, which is x plus 4, left and right margins. And this function needs a label, and we're going to call this label area. Does that make sense to everybody? Okay, well, let's multiply this out and see what we get. We get this right here, and we observe something. Does anybody see a particle over here that's also present somewhere else?
That's right.
X times y, that's exactly right. X times y is 50, so it makes sense that I could replace this with 50 plus 4y plus 8x plus 32. And there we go. So that's pretty cool. I've got an area function that I'm trying to minimize, but I still have two variables. And because I still have two variables, I'm still going to need to do some substituting. Exactly. X is equal to 50 over y. He's choosing to substitute for x. He could have chosen to substitute for y. Both of those work. Wow. Just like it worked. There we go. So I'm going to replace x with what it is, which is 50 over y. And so this gives me area as a function of y. Question, domain. What's the smallest y that I could use? Theoretically. Zero is the smallest that I could use. I have really skinny printing. So my domain starts at 0. No.
Are you including the margin in this or not? Because
This is where the diagram really clarifies that for us. The diagram clearly shows that y is this distance right here, which does not include the margin. Yeah,
So y cannot equal to 0.
correct. And so that's why I put the open boundary in there. Yeah, that's right. Y could be as large as I want to if I'm willing to make x skinny. So that we have a domain of 0 to infinity. Once again, an open, unbounded interval, we're going to have to use an argument from the sign of f prime. And so I've got my area function here. Let's get critical points. A prime is equal to 0 plus 4 minus a times 50 is 400 over y squared. Set that equal to 0. Can you solve this equation in your head? I bet you can. What value of 10? That's right. And if y is equal to 10, and x is equal to 50 over y, then x is equal to 5. But does this legitimately minimize the amount of paper that we're going to use? To check that, we need to make an argument from the sign of a prime. So, I'm going to take a y value that is less than 10, 5, how about 1, and plug it in. And when I plug it in, I get 4 minus 400. That's definitely a negative number. And I'm going to take a y value that is larger than 10, 100. Plug it in. 4 minus 400 over 100 squared, definitely positive. And therefore, we can conclude, here's the magic language, since a prime is negative for x less than 10, and a prime is positive for x greater than 10, that means, excuse me, I said x, it's y, isn't it? And that means that area of 10 is a minimum. And the dimensions, which are the length and width, are 5 by 10. X equals 5, y equals 10. Another way of putting it. Does that make sense to everybody? How this works? Good. Tomorrow we're going to do some more. See ya.